Hello, everyone. Welcome back to our last lecture of the series on geometric interpretation for the delta theorem. And thanks, Sean, for giving such a great lecture series. Okay, so I'm not going to take too much of your time, Sean. Go ahead.
Okay, thank you again for letting us do this. So I might have bit off too much, too much or more than I can chew on this in this lecture because I want to introduce affine Springer theory and explain how that connects with everything and how the combinatorics fits in with general T. But so I might have to start skipping stuff at the end. We'll see. But still feel free to ask questions, of course. So last time I set up this theory of Born-Macpherson of partial resolutions of inverse. Um, and basically between this Springer resolution, you have these partial resolutions and alpha tilde. They're not smooth, but instead rationally smooth. And then you can break them up into strata and then restrict your map to that strata. And what I'm calling the Born-Macpherson variety or Born-Macpherson fiber is a fiber over that stratum. Um, and we saw how, um, so analyzing the maps in this diagram gives you an isomorphism between a tensor product of cohomology groups and on the left-hand side and this cohomology, or not exactly cohomology group, but an isotypic component of the cohomology of a Springer fiber, which we can describe combinatorially. Um, and yeah, I wanted to point out if you don't have this rationally smooth condition, there is still something you can say, but you'd have to phrase it in terms of intersection cohomology rather than cohomology here. But if this condition holds, we get this nice isomorphism. I was corrected last time. I stated the symmetric group action a little bit too generally. But the case that we care about is when this tuple of partitions is a bunch of singletons and then some big partition. The symmetric group still acts on the first n parts, basically. You still have like a complete flag at the beginning, and you still have a Springer action there, basically by restriction of this relative Weil group. Um, and so how do we use this to prove this symmetric group, or sorry, symmetric function identity? Um, so I got part of the way. This left-hand side I'm interpreting as the Frobenius characteristic of the SN action on these delta Springer varieties. The right-hand side I'm interpreting as the Frobenius characteristic of the usual Springer fiber. Um, and then this skewing operator is what comes out of taking this isotypic component here. Um, so first of all, you can check that this delta Springer is this particular Bohr-Macpherson fiber. Second of all, you can check the rational smoothness property. It just comes down to some particular combinatorics of tableau. And I think I wrote an explanation for why this is in the notes. But for example, if you have tableau of a rectangular shape and you allow your content to be um, inside of the rectangle with one extra row, so just basically just restricting the length of the content, then there's a unique tableau with that shape and content. So here it is in that case, oops, content 3, 2, 1, and shape this rectangle. There it is. And It's a fun exercise to figure out why in general. Um, and then how do you translate the skewing formula to the Borel-McPherson setup? Just translating Borel-McPherson's isomorphism, here's what you get in our particular case. And we're just taking the isotypic component when you restrict down um, to just acting on the last part. Um, and so on the right-hand side, or sorry, on the left-hand side, we get the cohomology ring of the thing we wanted, the delta Springer. We have this coefficient that's sitting in a single degree. And on the right-hand side is this isotypic component thing. Sn acts on both sides here, and trivially here. And then to combine all of this, complete the following exercise, that if you have a symmetric group acting on some vector space and a partition of smaller size, and you take the isotypic component of the restriction for that partition, um, it's related to the corresponding Schur skewing operator um, with precisely this equation where the dimension of the irreducible pops out on the right-hand side. And essentially what happens is when you take Frobenius of both sides, um, then this dimension cancels with that dimension, and you get the then you get this equality. And I just wrote it out down here. There is a grading shift. Um, so here there's a plus 2D grading shift, but it basically goes away when you reverse everything. Um, I also wanted to say,
Oh,
I guess
Sean,
Maria already mentioned. Yep.
sorry, Nikita has a question on the chat. He asked, what is the symmetric regression on the left side? Is it still SM?
So here, um, so we're restricting down to a S size of mu cross S si M minus size of mu representation. So when you take the isotypic component, S M minus the size of mu still acts there. And here, SM acts. So this is, if you want to check, in terms of symmetric functions, this is degree M. This reduces degree by size of mu, and this is degree M minus size of mu, as it should be. Okay, so I wanted to point out that unlike, well, yeah, Maria already mentioned this in her talks, but unlike with the full rational shuffle theorem, when you restrict to t equals 0, for this case, you do get a sure positive expansion on this side because it's just a Hall-Littlewood polynomial, and those expand in terms of sures, for example, using the Cochard statistic. And then you can take that sure expansion and skew out all of the sures by this shape, and then you can expand back into sures. And so what you end up with is a new Schur expansion um, for the left-hand side for delta theorem at t equals 0. And we write this in terms of objects that we'd like to call battery-powered tableau. And Maria created this nice image to represent that, where you're plugging in a rectangular partition down here and computing the co-charge of the whole thing. So it kind of adds extra charge in a way. Okay. Are there any other questions on that part before I move on? So I wanted to spend the remaining time talking about affine spring fibers and the full T version. Um, so instead of vector spaces, we're going to be working with modules over formal power series. So instead of just taking the field of complex numbers, we're going to be taking the field of Laurent series. So those will basically be our coefficients now. So yeah, what this means is so Laurent series, and these are formal power series. And what I mean by that is you're allowed to have infinitely many terms with non-negative powers for formal power series. And on the Laurent series side, you can start at any arbitrary negative number. Uh, any arbitrary negative coefficient of or negative power of epsilon. This is for any any integer, positive or negative. Um, and a lattice is, and now let me turn to my notes. So a lattice is an O submodule of this vector space of Laurent series to the nth power that has rank n as a module over O. Um, by submodule, I mean, essentially you can just interpret it as epsilon applied to lambda is still inside of lambda. But I'd like to make kind of the following visual simplification. Um, so I have this visual representation of um, a basis of this vector space. It's not an actual basis because we should be allowing infinite terms. It's called what's called a topological basis of this vector space. But anyway, we can kind of think of it as a basis. And to specify a lattice, one way we could do that is just by selecting one thing from each column. So basically selecting an epsilon power for each basis vector. And here like epsilon to the I, E, J, those span the ith or the jth factor of this vector space as I ranges over all integers. So to specify a lattice, we can select one in each column, and then when we take the O span, it's basically just taking the down set. All epsilon power is higher than those. So an example of a lattice is the O span of epsilon E1, epsilon inverse E2, E3, epsilon squared E4, um, epsilon squared E5. And so, for example, like epsilon squared E3 is in there because it's below. So that's a lattice. And then a complete flag of lattices is kind of what you would expect, given the definition of complete flags of vector spaces. So it's a nested sequence of lattices um, where the dimension or the quotient of the successive lattices is has dimension one as a C vector space, except with the following cyclic property that when you get to the nth piece, this is just the same thing as epsilon applied to the lattice that you started with. Um, I apologize to all of the Schubert people, and also to everyone following along that, yeah, usually when we do vector space, flags of vector spaces, we index going up, where the larger the index, the larger the subspace. But for particular reasons, I like indexing flags of lattices going down, because it helps me match it up with the combinatorics and with affine permutations later. So sorry for that notation change, but hopefully that's not too bad. So for example, for example, how could I make a flag of lattices? I could start with this lattice on top that I already selected. And then one by one, I can uh, decrease the size of the lattice by removing some things from the top. Um, so as a first step, for example, where did I put this? Um, yes, sorry, yes, thank you. That was a typo. Yes. Um, yeah, I minus one is the larger thing. Thank you. Okay, so how could I make a flag of lattices? For example, um, I could remove E3 from the lattice. So maybe the black is lambda 0, and then the red is lambda 1, where I've removed E3. And then my new generator of the lattice is epsilon E3. And then I could remove epsilon E1. Um, and now my new generator, now my new generator is epsilon squared E1 and so on. So another way of specifying this is just specify the order in which you remove things. So instead, I might encode this information by starting with the top things and then putting numbers next to the things that I've removed. So maybe I put a 1 next to this E3 because I removed it first, and then a 2 next to epsilon E1 because I removed it second, and then say like remove that one next, and then that one, and then finally that one. And then if you notice, once you do this n times, um, what you end up with is epsilon times what you started with. So this cyclic condition makes sense. So the affine Grassmannian, at least for GLN, is the space of lattices. So I'll denote it by this tilde notation. And the affine flag variety is the space of complete flags of lattices. Um, Another way that you can encode this is with matrices. For any complete flag, does there always exist a Schubert basis such that it is obtained as in your example? Yes. Uh, Uh, yeah, you can turn this into, or are you asking about Schubert bases or um, maybe the question will be answered by the topological basis. Uh, so in general, you will have like sums of things. I guess, I see. Yeah, I'm. This picture was just to illustrate. Essentially, these are the fixed points, the torus fixed points of the space. So like having ones and zeros in your matrix. But you could have sums of things like I could have added like, plus 3 epsilon E4 or something. But then I'd have to change something about E4. Actually, no, I could just do that. Um, so um, yeah. So maybe the next comment will make a little bit more sense. So you can encode these with infinite periodic matrices up to some column operations, just with like normal Schubert cells, um, and just like with normal complete flags. So essentially, so this was the picture that I drew before. But then you can define like this topological basis, we can index it by integers by saying define EI. So for any integer, by the rule that if you start with some EJ and you apply epsilon to it, epsilon to some power to it, then make a new vector called or with index j plus n times I. So essentially, as you multiply by epsilon, it shifts the index by n. And there's this sort of cyclic property to the indices. You really want to think of it modulo n, and then the factor of n tells you which epsilon power. So I could encode this one as a matrix by saying, okay, since I have a 1 here, put a 1 in the E3 row in the first column. So I've indexed the columns by the parts of the flag, and I've made a row for every single integer. Well, modulo not being able to draw infinitely many rows. So I would end up with a 1 in the E3 position. And then the second one is epsilon E1, which goes in the E6 or epsilon E1 row. So that's why I have a 1 there, and so on. And then you could consider Schubert cells where you interpret these ones as pivots. And since my flag is going down in dimension, I would be using these pivots to eliminate to the left. So for example, I could add some arbitrary coefficients like here and here because there's nothing to the right of it. The ones you would kind of have to backtrack in the flag to see that like this the pivot that's supposed to be in E4 is coming from where is it? It's coming from down here, but then you have to kind of shift it back up twice to see that one. Um, so there's a notion of Schubert cells in this setting. Okay, so one of the major differences between usual flag variety and these affine flag varieties and Grassmannians is that they're both infinite dimensional. And in fact, they have infinitely many connected components. And the connected components are indexed by the integers. Um, Reason being that the fundamental group of GLN over the complex numbers is isomorphic to Z. Um, and the extra parameter is sort of like a loop rotation. So concretely, given, oh, sorry, and I forgot to say, there's a Gmod B way to write down these spaces. So if you encode all of these things in matrices, um, you can realize both of these things as quotients, like with the Grassmannian and the complete flag variety. So the affine Grassmannian, alternatively, you could think of this as invertible matrices over this Laurent series ring, and then modulo invertible matrices over formal power series. And for complete flag varieties, there's a Gmod B like construction where you're just modding out by a different subgroup. The You're modding out by what's called an Iwahori subgroup. So it's the um, maybe I will not write that down because it might be confusing. Okay, I'll just say I is what's called an Iwahori subgroup. It's the analog in the setting of a Borel subgroup of upper triangular matrices. Just encoding this idea of um, doing column operations. There's some subgroup you can quotient out by that encodes the column operations. Okay, so how do you see these infinitely many connected components? So given a matrix representative, G, a matrix representative, when you take the determinant of G, you'll get some Laurent series, because that's what the entries are. Um, so you'll get some AM times some power of epsilon, and then some other coefficient times the next power of epsilon, and so on. Uh, and let's say AM is the leading coefficient, then this integer m indexes the connected component that you're in. Um, and now there's a notion of Springer fiber in this setting as well called the affine Springer fiber. And instead of considering, matrices over complex numbers, now you have matrices over Laurent series. And you can just write down the same definition. So lattices, so that now there are two versions, one for lattices and one for complete flags of lattices, and you could have partial flags of lattices as well. So it's given by all lattices that are preserved by this operator gamma, whatever it is. And the complete flag version is kind of what you would expect, where each piece of the flag is preserved by the operator. Um, In this talk, I all of the operators will have this property called nil elliptic, which essentially means that as you keep applying the operator, um, the epsilon powers are predictable, uh, in the sense that the limit, so the limit of gamma to the mth power as m increases is zero. By that I mean as you keep raising this operator to higher and higher powers, the epsilon coefficients in the matrices keep getting larger. There's no like constant hanging around. Um, so for example, like I could have a diagonal matrix with all positive epsilon powers. That would be nil elliptic, but I'm not allowed negative or zero powers for diagonal matrices. Um, and these two spaces are related by a projection map. So you can take complete flags and project them down to lattices just by remembering the zeroth piece of your flag. Um, and why would you want to do that? Because the fibers are the fibers of this projection map are recognizable as the usual Springer fibers. So each fiber of pi is isomorphic to a usual Springer fiber. Um, so if you take the preimage of some fixed lattice, you get essentially you're filling in a flag uh, between epsilon lambda and lambda, which means that you're just taking complete flags in a fixed vector space. Um, and then this gamma preserved condition just translates into the fact that um, when you think of gamma as an operator on the quotient space, lambda mod epsilon lambda, that's a finite dimensional operator, and because of this nil elliptic property, it has to be nilpotent on that finite dimensional vector space. So we do get a Springer fiber, and you can kind of think of this as like, yeah, the map is this map is kind of encoding families of Springer fibers. And as you change this base flag, you're seeing how gamma acts on different quotients. And therefore the Springer fibers could change as you change gamma, or sorry, as you change lambda. Um, and essentially, because each fiber is a Springer fiber, and because the symmetric group acts on the cohomology of each fiber, you can kind of collect all of those actions into one action on a sheaf, which then translates to an action on the space itself, or the cohomology of the space itself. For this talk, what I really need is homology. Um, the reason being that, uh, I mean, some of these spaces are infinite dimensional, and you kind of have to be careful with cohomology. But also, I'll be working with some non-compact spaces, which essentially means that what's called Borel-Moore homology is a better homology theory to work with. So I've stated it here as there's an SN action on um, this Borel-Moore homology. If you don't know what Borel-Moore homology is, you can just think of it as homology. Um, there's even an action of the extended affine Weyl group, but we only need the SN action because we want Frobenius characteristics. Okay, so what does this have to do with combinatorics? Hikita proved the following theorem, that if you take a particular gamma operator, one which is zero on the diagonal, but then epsilon's on the anti-diagonal, and then an epsilon squared in the upper right, and then look at the affine Springer fiber, you get essentially the combinatorial formula in the shuffle theorem. So there's one caveat here, which is I defined affine flag varieties and Springer fibers for GLN, but he was actually working over SLN. Um, but you still have an action of the symmetric group, and you can compute its Frobenius characteristic. And it matches up with the combinatorial side of the shuffle theorem, what you get by applying this operator nabla to En, but then up to these two operators that we saw before. Basically, tensoring with sign and reversing the coefficients, the Q coefficients. Um, and so here, just like before, Q is homological degree. T is a bit harder to parse. It's coming from a filtration of down on the level of the affine Grassmannian. Um, but then that filtration gives you a grading, which you can then interpret in terms of T, in terms of this area. Um, and I wanted to give a shout out to the Skorsky-Mazen-Vazirani paper, which gives a nice alternative proof of this fact. And in fact, their proof is the one that we generalize in our result. So to state our result, instead of this n by n matrix, we consider the following extension of that matrix, essentially. So instead of, uh, we're basically putting that same matrix into a block matrix, except instead of epsilon squared, we have a zero here for some technical reasons. Uh, and down here in the other side of the block is just an identity matrix. Um, and the dimensions of this matrix, and of course these are zeros. That's what I mean by block matrix. And the dimensions of this matrix, this anti-diagonal one is k by k, and the whole matrix is worked out to be this familiar number, the height of our rectangle, k times n minus k plus 1. And you can check uh, this gamma is nil elliptic. And you can check what you get as you raise the power of gamma. And instead of computing the homology of this whole space, uh, or sorry, instead of computing the homology of the entire affine Springer fiber over GLN, we define the following subspace of the affine Springer fiber. So we're looking at yes, we're looking at complete flags of lattices in the affine Springer fiber for gamma. In this version is the GL version, unlike Kikuda's result. Um, such that two conditions hold on the 0th piece of the lattice. By positive part, so we call these the positive normalized part of the affine Springer fiber. And by positive, I mean that lambda 0 is is contained in what's called the standard lattice. Inside of, so all of our representatives are only use non-negative powers of epsilon. That's what it means. And by normalized, so that's what the 0 is for, we need this extra condition that it's not too far inside of that lattice. It's so that it's not inside of what you get by applying epsilon to the first factor. So essentially, it's a way of taking this infinite dimensional thing with infinitely many components and restricting it to a finite dimensional thing so that we get finitely many terms in our Frobenius characteristic. If you want to think of this in terms of matrices or leading terms, essentially what this means is that E1 appears as a leading term in lambda 0. And I mean, and not epsilon lambda 0 anyway. Uh, yes. And so the result is uh, if you take the homology, and I really mean Borel-Moore homology here, of the space, there's an S k times n minus k plus 1 action on this thing. And when you take the Frobenius characteristic, you get the combinatorial side of the rational shuffle theorem. And here, our Q is the same as Ikita's, its homological degree, but the T is a little bit more transparent because it's just coming from this natural grading by connected components. Are there any questions on that? I will draw some pictures soon. Okay, so how do you match this up with the combinatorics? Um, so I kind of already gave you an idea of what do torus fixed points look like in these affine Grassmannians. But when you have this gamma operator, what does that mean in terms of the diagrams? Um, so here I've kind of only drawn the positive normalized part of the vector space. So there's other stuff down here like epsilon E1, epsilon E4, and so on, but we don't need any of that information for the diagram. And and I've drawn arrows here to represent the action of gamma on these vectors. So if you take this matrix description and write it out in terms of basis vectors, this is what it does. Um, so how could you pick a lattice that's preserved by this gamma operator? Essentially, what you do is you pick, so we're still picking vectors in each column, except I like to call these the gamma strings. Um, what you get by successively applying gamma. And as you move to the right, this gamma preserving property means that as you move to the right, you have to stay on the same gamma string or jump up to the next one or jump up two like you can either go right or you can jump up to a higher string. So I could take this partial string and then jump up to E8 and then continue on the second gamma string, and then finally jump up to the last gamma string. And then my lambda would be, the epsilon span of everything below it. And to convert that into a Deke path, what you do is take each gamma string and straighten it out and think of it as like the first, second, and third column of this diagram. So since I took one, two, three, four, five things in the first gamma string, I will go up five times in the first column. Since I took one, two, three things in the second gamma string, I'll go up three times and then over. And then I have one thing in my third gamma string, so I go up once and then over. So that's my deep path. So there's a bijection between torus fixed points of this space and deep paths that lie above this diagonal. And when I introduce this extra data of a complete flag of lattices, again, I'm just putting a permutation on these bubbles that I've chosen for my lattice, but with the property that as you go down the same string, the labeling has to increase. So it increases from 3 to 5 to 6 to 8 to 9 on the first string, and then you can kind of reset to whatever you want to. And that converts exactly into the parking function or word labeled the strictly increasing condition on parking functions. So we just record those numbers in each column and we get a parking function. I also wanted to mention there's a third bijection, another bijection, where you can interpret all of this in terms of affine permutations. So this might look a little bit familiar to people who are familiar with rational shuffle theorem, um, or people who have read the Gorski, Mazin, Vazirani paper. Essentially, what I'm doing here is I create this rank table of each cell in my diagram that's above the diagonal. And it's essentially recording what gamma is doing to these indices. Um, so for example, the 147 here corresponds to what gamma does to these three vectors. And then here is um, 11, 14, and 7. Yeah, 11, 14, and 17 if you do the indexing shift. So in terms of ranks, what gamma does is you can kind of think of this as broken up into chunks because we're in this integer slope case. Um, once we pass through an integer point, like you have these repeated blocks. And as you go upwards within a block, you're just adding k to the rank. That's what gamma does to the indices. And then when you go past a block, you add k plus 1 instead. Um, and then as you go towards the right, you're just adding, or sorry, you're subtracting the height of the rectangle. So -9 in this situation. Um, and then you can combine these two pieces of data, the rank function for gamma and the parking function, um, and turn this into an affine permutation by saying, okay, where's the up step labeled 1, and what's the rank of the cell immediately to its left? It would be this cell. So let me repeat the ranks. So this cell is rank 8, 14, 11, 7, 4, 1. Up here I have 12, 15, and 9. And the affine permutation just records these ranks in the order that they come in this parking function. So so essentially 1 maps to 8. So 8 is the first thing in my affine permutation. 2 maps to 12, and then 3 maps to 1. So I have a 1 there, and so on. And essentially the positive condition corresponds to, we call this the window of an affine permutation. It corresponds to having only positive integers in this window. And the normalized condition corresponds to, well, you always have to start with this up step here in the lower left. So you always have rank 1. And in terms of the affine permutation, it just means that 1 has to appear somewhere in the window. Um, And you can write down exactly which affine permutations you get when you do this bijection. Any questions on these diagrams? Okay. So how do you get, so to end things, how do you get a geometric interpretation of the delta theorem? You take these definitions like before, and you just affinize it. You interpret it in terms of affine flags. So before we had the Borel-McPherson variety, now we can make that into an affine definition where we have flags of lattices, or partial flags of lattices, maybe indexed by some composition alpha, um, preserved by this some gamma operator, but with the same Jordan type conditions on the quotients of the flag. So this replaces our the previous Jordan type condition. And in the specific case, when you take um, this lambda sequence and the gamma operator from previously, the Borel-Moore homology of this variety has an SN action, just like the Borel-McPherson variety before. Oh, sorry, and there should be a tilde on here for affine. And you get exactly the delta conjecture or delta theorem combinatorial formula, but up to this reversal in tensor by sign. And the proof of this fact is just um, it's almost the same as before, except we have to be a little bit more careful about the skewing identity, and we have to check more rational smoothness conditions. So first of all, we prove the first theorem just using an affine paving, computing cell dimensions. Um, the second step is to prove this more general rational smoothness property, essentially that if you take this Bohrholm-McPherson variety and map it down to the affine Grassmannian, the fibers will be some varieties of complete flags. Some of them will be the Delta Springer varieties, some of them will be a little bit more general, but you always get a variety that Jake, Alex, and I have studied previously as a fiber of this map. So it's composed, this map is composed of things that we understand well. Um, and once you check this rational smoothness, you get a geometric version of the skewing formula. Connecting these two Frobenius characteristics, these two varieties. And then you just combine all of these things to give you that the Frobenius characteristic is, well, it's the skewing formula where you consider complete flags, and then you can replace the Frobenius characteristic for complete flags with the rational shuffle theorem. You can move the skewing inside, but you have to transpose the partition, so n minus k becomes k minus 1. But then this is exactly the skewing that showed up in Maria's talks. Um, that gives you the delta theorem symmetric function. So that's the sketch of the proof of this theorem that these sorry, affine Bohrholm-McPherson varieties geometrically represent the delta theorem. And with the last 30 seconds, I'll just say thank you for listening. Thank you to the organizers for letting us do these talks. And thank you to the audience for all of the great comments. And as a bonus, so I asked ChatGPT what it thinks about Springer theory, and I asked it to generate some images. So this is what ChatGPT thinks a sure skewing identity looks like, which is not so far off. This is what it thinks a Springer resolution is, torus mapping to Borel, um, which has some of the components, correct components. I'm not sure where it got this from. I think it was just picking something out from a paper and maybe chose the wrong chose the wrong equation. And then this is what it thinks an affine Grassmannian looks like. So if anyone has an explanation for why that should be an affine Grassmannian, please let me know. And then just as an extra, I asked WhatsApp AI stickers to generate an affine Springer fiber, and this is what it came up with. I think those are maybe, I think that's yarn wrapped around a puppy. So yeah. And yeah, if anyone understands why, just let me know, please.
Okay, let's thank our speaker, all those. Uh, and any questions for Sean? Actually, I had a kind of a big picture question, just so Haymann's original thing was that Nobly N has this Hilbert scheme interpretation. But if you let K equal N in your scheme, you get something different, right?
Right. So, right. Even for k equals n, yeah, we're getting these affine Springer fibers. And this goes back to Hikita's theorem.
Uh-huh.
And yeah, it's just a different geometric
I see.
interpretation.
So it
And
kind of extends the Hikita angle.
right.
Do you know any, have you thought about any connection with the Hilbert scheme?
I'm still trying to understand that.
Okay.
Right. So Mark does have a conjecture in one of his papers uh, that there is a particular vector bundle on the Hilbert scheme such that higher cohomology vanishes, and the zeroth cohomology of that vector bundle should match up with the delta conjecture. But I still don't understand if there's any connection between, if there's any direct connection between these affine Springer fibers and the geometry that Mark was doing. And I'm not sure if anyone really understands this, even in the k equals n case, that well.
Okay, so any other questions? Comments?
Sure. Maybe I'll ask at the very last bullet, you mentioned the work I was doing with Satoshi and Brendan. Do you have any
Yes.
initial thoughts as to what the connection could be?
I mean, right. So Field's conjecture is somehow summing over k. And like if I go back to what I was doing before at t equals 0, um, we had these rectangles increasing in size. Um, and so k was the number of rows, which is sort of like increasing your vector space, your like base vector space. And so, I mean, I want what I want is like, yeah, maybe there's some kind of union where k equals 3 is sitting inside of this particular three-dimensional vector space. But I still don't have any concrete ideas.
Okay, well, let's thank Sean for a great series, Maria. And so what's next in IPAC? We're taking Tuesday off, and then Thursday we begin a series of 3 talks on a new paper, which is a joint paper with Masu Yu, Jae-Sung Oh, and I on kind of a combinatorial, some problems with there's a new parameter we put into the chromatic symmetric function for unit interval orders. Uh, Wax and Tresian introduced. And anyway, so that's that. And then there's a kind of a long break uh, for almost a month. And there's the FIPSAC conference in there. And then Hikita is scheduled to give a series of talks on his proof of the Stanley-Stembridge conjecture starting August 5th. So anyway, we'll see you next week perhaps. And in any case, have a good summer. Bye.
Thanks, everyone.
Thank you.